Hello. If I sound a little bit different today, it's because I just don't feel good. But I'm kind of pre-recording this in case I am not feeling good. So I'm going to record this so that you guys have something to view. Okay, when you're learning the next section. Have your half sheet out. It's under my MathLab course tools document sharing. It was on the other side of 3.3. It's basically going to look like this. Okay, so have that out. I will refer to it, or it's on page 212. Okay, but in this section, just so you know, in Unit 2, we just finished up Chapter 3, graphs, lines, and functions, and now we're going to start Chapter 4, which is basically 2 lines or 3 lines, and where do they intersect. So when it's called a system of linear equations, that's what it's talking about. So today in section 4.1, we're going to cover systems of linear equations in 2 variables. And these are the different objectives that we're going to go over. So an ordered pair is just a point on the graph. And so when we're talking about the first objective, is that the point where the 2 lines meet? Then that's called a solution. We're going to solve today by graphing. And then we're going to solve by substitution, and then we're going to solve by elimination. So the second objective is more picture, and 3 and 4 is algebra, and then at the end is solving special systems. Now, anytime in this recording, if you want to pause it so that you can slow it down a little bit, or take notes, or do the problem on your own, feel free to do that. Okay, as an overview, this systems of linear equations in 2 variables is kind of looking at a word problem. And this word problem doesn't really describe it on the right-hand side, but it's talking about the sales since 2000. So in 2000, digital camera sales were actually lower. The blue one was lower than the red one, the digital camcorders. But in about 2001, somewhere in 2001, the sales were the same. That's where the 2 lines intersect. After about 2000, somewhere in the year 2001, then digital cameras took off, and digital camcorders, their sales went down. Okay, so this is a perfect example of where you could have maybe 2 lines intersect, and they might ask you, okay, where's the solution of the system? Where was the sales exactly the same? And you would say somewhere in 2001. Okay. Now, in the first objective, they're going to give us a point or an ordered pair. Okay, they want to know, is it a solution of the system? Okay, so let's look at the first example. So it wants to know if this ordered pair or point is a solution to this system. I usually call my lines A and B. So what I'm going to do is I'm going to substitute this point into equation A, and we're going to substitute it into equation B. So instead of 2x plus y equals negative 6, we're going to say 2 times the x value is negative 4 plus the y value is 2. Is that equal to negative 6? And we're going to see if that's true or false. So negative 8 plus 2, does that equal negative 6? Yep, negative 6 equals negative 6. So what that means is the point negative 4, 2 is on the A line. Okay, now let's look at B. So B's equation is x plus 3y is equal to 2. So we're going to substitute in. X is negative 4 plus 3 times y is 2. We're going back to this point, is equal to 2. Is negative 4 plus 6 equal to 2? Yes, 2 is equal to 2. So we say that the point negative 4, 2 is also, on line B. So because both of these are true, this point is true, this point is true, then what that is saying is the point negative 4, 2 is the point of intersection. And what intersection means is where the 2 lines meet. That's what it's talking about, point of intersection. If I were to graph these two, and I'm just going to do this very, very quickly, but if I were to graph these two, I have done this on my paper already, so I'm not going to put in a lot of detail. But if I graph equation A, and of course I didn't label it. Okay, equation A looks like this, or line A. And then line B looks like this. And this solution, 4, 2, because it said yes in both, it has to say yes in both, then negative 4, 2, and I know this is not drawn to scale, but that's the point of intersection. That's the point where the two lines meet. And so you have to have yes for both. If you have a no for either, then you would just stop and say no. Okay? All right, let's look at another problem. And again, if you feel that that you need to slow down, then just pause this recording. Okay, so if you notice, this one's a different problem. We've got 3, negative 2, it plugged it into equation A, and it ends up being true. So that means it's a point on that line. But if you plug it into equation B, that's false. So overall, you would say it's not a solution of the system. It's not a point on this line. So if it's not a point on a line, then it can't be the point of intersection. Okay, now we're going to solve linear systems by graphing. Okay, so we're going to actually graph these two. Okay, so how you graph it is kind of your choice. Remember when we graphed before, you could do a t-chart, you could put it in slope-intercept form, you could find the intercepts and so forth. But I'm going to call this equation A and B. In equation A, 2x plus y is equal to negative 5. I am actually going to solve for y. So I have negative 2x minus 5. So what I just did for that is I put it in slope-intercept form. Because now what I can do is I can go down to negative 5. And you want to try and keep these evenly spaced. Okay, and so this is like saying all right, let's do this in a different color. Let's say this is orange. I'm start off at negative 5, I'm going to go down to right 1, or I can go up to left 1. So I have now this line here, and I'm hoping this turns out because I didn't use a nice graph. Okay, equation B is negative x plus 3y is equal to 6. Well, I'm going to graph this a little bit differently. Let me do t-charts. So let's say I put 0 in for x. Negative 0 plus 3y is equal to 6. 3y is equal to 6. Y is equal to 2. So why don't I point to 0, 2? Well, let's put 0 in for y. So you have negative x plus 3 times 0 is equal to 6. Negative x equals 6. Or x equals negative 6. So I'm going to graph B with green. So 0, 2. Negative 6, 0. So I am now going to connect the dots there. Now what happens here is where the two graphs intersect. Now this is supposed to be at, will you believe me? Oh, please believe me. This one's actually supposed to be intersecting at, and I graphed it a little bit off, negative 3, 1. So something happened here where my graph is not exact, you know, and that's what's going to happen. So let's do that's negative 3 and this is 1. So that's my solution, is where they intersect. So when I ask to solve this system, your solution is going to be a point now, negative 3, 1. That's your solution. Okay, and that's what you would type in. And that's how you graph those. And they're going to probably have nice numbers that work out there, so you don't have to worry about fractions. Okay, and then the book goes in and does it. So it's a little bit cleaner here. You know, they solved it a little, they put both of them in slope-intercept form, but they solved it and got negative 3, 1 as well. So their graph's a little bit nicer. Now, on page 212, they go over, this is what we were just talking about. If two lines intersect at a point, that is your solution, is the point of intersection. And you can read it up here. It intersects at a single point. The system is called a consistent system, and the equations are independent. Now, if your lines are parallel, you're not going to have any solution because they will never touch. So if they never touch, there's no solution, but that system's an inconsistent and the equations are independent. So they have the same slope because they are parallel. Never touch, same slope, parallel lines. Now over on the right, you can't really tell right now, but maybe one line is orange and the other line is green. Well, those lines are on top of each other, so you would say this is the same line. So they have the same slope and the same y-intercept. Everything is the same. I should have said on the middle one there is same slope but different y-intercepts. Here's a y-intercept there that's different from that one. Okay, and for the green and orange one, basically what you would say is the same line. The solution is infinitely many solutions right there. And their type of system is consistent and the equations are dependent. So they might ask you those, just refer back to this chart. Okay, now we're going to get into objective 3. Objective 3 is going to solve the system again by what's called substitution. You're still going to get a solution as a point, but you're going to do it with algebra. Okay, and then the next one we're going to do is elimination. Okay, and then you're going to get a solution, x, y, that's going to be by elimination. So substitution is very used when one equation can be solved easily for another variable. Okay, so if you look at, and these are steps in the book, I kind of just skip them because I do my own steps. Okay, but if you look at this one, this would be a perfect example of substitution because x is solved by itself. X is alone by itself. I call them equations A and B instead of 1 and 2 because it's less confusion. But if you look at equation B, it's already solved for x. What I'm going to do is I'm going to substitute that into equation A. So your first thing is to solve one equation for one variable. That's your first step. So basically, equation B is already solved for x. Then your second step is to substitute that variable, and in our case, I'm just going to say x because it is x, into the other equation. So it has to be into the other equation, and for us, that would be equation A. So in equation A, instead of 5x minus 3y equals negative 6, I'm now going to substitute in, I just found x is equal to 2 minus y. So I'm going to substitute that in there. So I have 5 times the 2 minus y minus 3y equals negative 6. And then what I do is I solve for the variable. And in this case, it's y. So I'm going to distribute my 5. So I get 10 minus 5y minus 3y equals negative 6. 10 minus 8y is equal to negative 6. Subtract 10. Negative 8y is equal to negative 16. Divide both sides by negative 8. And y is equal to 2. Now, I'm going to circle that it's not my full answer. Remember, your solution has to be an x and a y. So what do I do next? I substitute. Now, I'm going to put this in parentheses because it's not always going to be y equals 2. So substitute that into either equation A or B. Once you get an answer, a number for one of the variables, you can do it either one. I'm actually going to choose B because it's already solved for X, and that's what I want to do. So I should say and solve for the other variable. So we have in equation B, I'm now going to put y in. I just found y, so I'm going to substitute that in for y. And I'm going to solve for x. So x equals 2 minus 2. Sorry, that's a little off. So x equals 0. Now, what is my solution? My solution is in the form of x comma y. So in this problem, I would want to say my x value is 0 and my y value is 2. This is the point where the two lines meet or intersect, 0, 2, and that's what you would put in for your answer. Okay, for right now, I'm just going to leave this alone. We will, if I can, I will record elimination in the rest of this section, but that is where we're going to stop right now. Okay.